Here are our solutions to homework set number 12 for ECE 463. This looks at Kalman Filters, basically a fuller order observer with a very specific H. So starting out, kind of as motivation, let's take a cart and pendulum system when I've got noise on the input, noise on the position measurement, noise on the angle measurement. How does that noise affect the system? Well, the first problem is use a servo compensator, same one we used in homework set number 11, and see how it behaves. So what I can do in MATLAB is say there's no noise coming in. I've got my servo compensator state. There it is. These servo compensator gains, Kx, Kz, my integrator, the servo compensator, no noise. My output is position, using full state feedback, using the actual states. With no noise, here's how it behaves. We go from -2 to +2. The observer actually kind of ignore that part. We're not using it right now. I've got a nice clean step response, about what I expect. What happens when you turn the noise on? So if I add the input as a disturbance 0.5 is the standard deviation, mean of 0. Position measurement has a standard deviation of 0.1 meter. So let's see what happens when I add noise. The observer, I'm just going to make 0. I'm going to get it out of the way. So here's the cart. There's the observer. We're ignoring it right now. The cart comes over, but now I've got disturbances on the input, the position measurement, and angle measurement. Cheating a little bit, I've also got the velocity and angular velocity measured exactly. But with the disturbances, kind of see it's being jostled around a little bit. That's how the noise affects the system. Okay, so sort of works. Now that I've got a control law, let's come up with a full order observer. Now there's a couple ways to do that. If I use pole placement, I tend to get fairly high gains. And I've also don't really know what to do with position and angle, so I'm going to combine the two. I've got position and angle, my new C matrix. Find the feedback gain H. What I really did is the position gain is this guy right here. That's the 1. The angle gain is 10 times bigger. So I'm just going to say that the observer gain from position to angle is always a 1 to 10 ratio. Probably not optimal, but that's kind of what I'm doing. I've got a problem. I want to use angle, but pole placement, the techniques we know only can use a single input. So combine the two somehow. That's at a 1 to 10 ratio. When I do that, I get fairly high gains. The closed loop poles are correct, but I have high gains. What the gains are going to do is add noise. So if we go back to the simulation, let's go back over here. I'm finding the feedback gain H using pole placement. My full order observer now my input's going to use the observer estimates rather than the states. I am going to update the observer with H times C times Y. There's the position plus noise minus the observer state. And I'll let the observer run. How does that work? So here you can see the red is the actual position. The pink is the observer state. There's a lot of noise on the observer. The reason for all that noise is the high gains on H. I found H using pole placement, which tends to give you fairly high gains. The net result is high gains times noise. Gives you that response. The plant actually isn't too bad, but the observer, the state estimate, is way, way off. So that's using pole placement. Suppose instead I used a Kalman filter. If I can find it. There we are. Kalman filter is just a fuller order observer, but it uses a very specific H. In that case, H comes from Q and R. Q is the input disturbance, So my input goes through the B matrix. It's BB transpose times the variance of the noise. R is the sensor noise. The standard deviation on the positions, 0.1. Standard deviations on angles, 0.05. Use LQR with that Q and that R, gives you a very specific H. What that H does is that gives you the best least squares estimate of the 4 states of the system. So trying that, what it kind of looks like is this. You go over here, and rather than using pole placement to find H, I'm going to use LQR techniques. Now when I do that, I'm going to have a 4x2 matrix. Both sensors are being used. Yeah, I think that's all I need to change. Let that puppy run. And now if you notice, the position, or the car position and its estimated position are much closer. That's the property of the Kalman filter. It is the best least squares estimate of the states, given the input, given the output, given the noise, given the dynamics. With better estimates, I get a much better behaved control law. It's still being jostled around. I still have velocity, angular velocity being estimated by the observer. Bounces it around some. In addition, a problem I have is my servo compensator right here. I am using the estimated position, or the measured position that has noise on it. If instead I did the estimated position, that takes out the noise. So let's make that the observer state the estimated output. If I run that again, it'll behave a little bit better. This kind of shows that even though I'm measuring position, I would rather use the estimated position than the measured position, just because a property of Kalman filters, or observers, is they act as low-pass filters. They help filter out the noise. So if there's noise on the sensor, I might actually want to use the observer's estimate rather than the actual measured estimate. Gives me a cleaner response. But again, that's the difference between a Kalman filter and using pole placement. It just gives you a lower gains for H, gives you better estimates of the states. Better estimates tend to give you better responses. This is kind of bouncing around because my noise levels are pretty large. Did that just so you can see what's happening. That's homework set number 12 for modern controls.